Hey everyone, welcome to another video. Now, today we are moving on to look at volume now. And as I've said before, as we progress through these courses, there's a lot of revision things of stuff we've already done. So in this year 10 measurement and geometry course, with volume, we are only looking at the newer things that we haven't seen before. These new shapes, such as pyramids and cones, which we'll be talking about in this video. Now, these two work in a very similar way. And I'm going to demonstrate this with just this little diagram I have here, as well as a little animation on GeoGebra, so you guys can hopefully wrap your heads around this and kind of see how we come up with this formula in the first place. Okay, so let's consider just a regular cube here. It has some height, some length, some width. Now, we talked about volume as the space that this fills up. The space this 3D solid fills up. So we find all of these volumes, you may remember, as taking some cross section. So here we're going to go with this guy down here. And let's call that A for the area. So our volume we get from doing the cross-sectional area. Here I've just done the base area of my cube, and we multiply that by the dimension or the side going away from that. So in this case, that's going to be our height up here. This is hopefully revision. If any of this is new to you, please look at some previous videos, because we're doing this assuming you've already got your head around basic volume questions. So our regular volume of some cube, for example, or any rectangular prism, is going to be just the area, the cross-sectional area, multiplied by the height. Now let's move on to actually looking at pyramids, because pyramids like this, for example, we call these square pyramids. And pyramid just changes based on whatever the base is going to be. Now, our pyramids have some type of height. They have this perpendicular height from the base of the pyramid to the top. And they also have a cross-sectional area down here. Cross-sectional area of A. But you can see that if we just went ahead and multiplied both these dimensions, well, we would just get this thing up here. So we need a different way to approach something like this when dealing with pyramids. Now, this is where we are going to visualize this through GeoGebra. And I'm going to put the link in the description too, so you can play around with it on your own if you'd like. But here I just have the regular cube, same one I've drawn in the video here. Now, we'll notice here, once we split this cube, that we have a couple of shapes that make up this cube, that fill this cube from the inside. Now, some of you, hopefully you can see I have a pyramid here, and another square pyramid here. Now, what's going to happen if we break this apart? So this cube here, I'm just going to break it, split, cut the ends, and open it up here. Hope we can all see that. And we can hopefully see that three identical, equal pyramids make up this cube. And one of these pyramids is just going to be the one that we had in our diagram, which has that same base area and height as the cube. So if we go back here, maybe I draw, actually I won't draw it in there, but if three of these, so if three pyramids make up a prism, here this was a cube, but it'll work in the other cases as well. If 3 pyramids make up a prism, we want to find out how many will 1 make up. So how many, or let's actually say how much of the prism will 1 cube be? How much, of the prism will 1 pyramid be, I should say. Will 1 pyramid be? Okay. We're asking ourselves a very important question here. Now, 3 of these pyramids, so 3 lots of my pyramid here, make up the volume of a prism. So the base area times the height. So 3 of my pyramids construct together to make a cube in this case, which the volume I get for that is my cross-sectional area or my base area times the height. So if 3 lots of a pyramid make up that volume, then one pyramid, I should say, makes up a third of that volume. And we can actually even show this in an equation. If I have 3 lots of a pyramid making up a cube, I can find one pyramid by dividing both sides by 3. I have 3 lots of something. So remember, when we solve equations, we can take the opposite operation to cancel this thing out. So that means that one of these guys is going to be a third of my area. So either 1/3 of my volume of a prism, or just the volume of my prism divided by 3. So this is the formula we have established for finding the volume of a pyramid here. Now let's actually apply this to a question. So if I have this question here, in which we have a pyramid sorry for the bad drawing, I'm just trying to do this as quickly as possible. I have my dimensions of 1.4 meters here, 1.2 meters here, and a perpendicular height from this base all the way up to the top of 1.3 meters. What is going to be the volume of this shape? So we said that the volume of a pyramid is going to be the third of a volume of a cube with the same base area and the same height here. So I can even go ahead and just draw a cube around here if we wanted to visualize this a bit better. Cube, or in this case it'll be a prism. Inside this space, my pyramid is going to make up a third of this volume of my prism that I have drawn here. So this guy over here. Now let's go and apply that, and we'll substitute in all of these numbers. So we'll do it slowly actually. So the volume of my prism, this big one on the outside, is going to be 1.3, my height, times my area of 1.2 times 1.4. So therefore the volume of my pyramid must be a third of that. So it's going to be this number, 1.3 times 1.2 times 1.4, divided by 3. So this is the main premise of this video, particularly with pyramids. My pyramid is always going to be a third of the volume of a prism with those same dimensions, with the same height, length, and width. And that is given by this formula over here. So applying that to this question, we get a total volume of, just rounded to 3 decimal places, 0.728 meters cubed. Remember, we have to put a cubed here because we are looking now at volume. We are looking in 3 dimensions. Now, a cone works in a very similar way. A cone ends up being a third of, have a think what shape it may be a third of. If I extended a height, this height down, and made a shape we've seen before, we're going to get a cylinder. Let's change this up a bit. My cone here with some perpendicular height, let's call that H, and cross-sectional area here, let's call that A, that is going to be a third of the volume of a cylinder. So if my volume of my cylinder is my area, my cross-sectional area times the height, or I can write this as pi r squared, because the cross-sectional area of a cylinder is always a circle, which the area of that is pi r squared times h. The volume of my cone with those same dimensions is just going to be my cross-sectional area times the height divided by 3, or it's going to be pi r squared times the height divided by 3. So that is how we can come up with the formulas for volumes of pyramids and cones. Now we'll just do one more question, just so we can practice applying this volume of a cone here. So I've drawn this guy over here, and this has a length from here to here of 23 millimeters, and it has a perpendicular height from the center going down here, making a right angle. It has a perpendicular height of 29 millimeters. We want to find the volume of this shape. Now, the volume, as we said before, is going to be the volume of a cylinder with the same dimensions. So pi times the radius squared times the height divided by 3. And now that we have this formula that's universal and we can use for any cones, we just need to substitute in the values. Now, I know my height, that's going to be 29, but this length here, this stretches from one side of the circle to the other side. So this here is actually the diameter, not the radius. The radius is going to be half of that. So it's going to be from the center stretching out to the end here. So half of 23 is going to be 11.5 millimeters. So this radius is what I'm going to be substituting into my equation. So that gives me pi times 11.5 all squared times 29. And all of that we are going to divide by 3. Or if you'd like to, we can write it in two different ways. It's either the volume of that divided by 3, or we can say 1/3 times pi times 11.5 squared times 29. There's two ways we can write this. Now, because dividing by 3 is the same as multiplying by 1/3, so we can present this equation in a number of different ways, but it's communicating the same idea to me. It's telling me that the volume of a cone is always going to be 1/3 of the volume of a cylinder with the same dimensions. Now, when we put this in here and round to 2 decimal places, this is going to give me approximately 4016.26 millimeters cubed. So, just to recap, the volume of a pyramid is going to be the volume of any prism, which is the cross-sectional area times the height divided by 3. So it's always going to be 1/3 of the volume of a prism with the same dimensions. So the volume of a cone now is the volume of a cylinder with the same dimensions. So a cross-sectional area, which is pi r squared, the area of a circle, times the height. And my cone is 1/3 of that. So we take that volume and we divide it by 3.